Friday seminar. It's a special pleasure to have Outi Tammisola as the speaker today. And Outi got her PhD at KTH, did a postdoc at Cambridge, and then took up a faculty position in Nottingham before returning back to KTH, where she's an associate professor now. So it's very nice to have you as the speaker today. And Outi is going to tell us something about complex fluids. So Outi, please.
Thank you. I will try to share my screen.
Yep.
You see something and let's... Okay, do you see the full screen?
Yep, yeah, we can see the full screen, thanks.
Okay, great, you never know. Okay, so thanks for the introduction and thanks for inviting me. So I'm going to talk about my recent work, which is on, or the recent work of my group, rather, which is on numerical simulations of two-phase complex fluids. And you see some examples already on the first slide on low Reynolds numbers and at higher Reynolds numbers, where the non-Newtonian flow character makes a significant difference in the flow features. So I thought that I would first give an introduction to the kind of complex fluids that we simulate and the challenges that we get in, or anyone will get in the direct numerical simulations when trying it. And then give just two examples of the kind of studies that we do. So the first is a yield-stress fluid flow through a porous medium. And the second is effect of viscoelasticity on bubbly flow with surfactants in the turbulent regime. And there is many other studies we have done as well, but I just took these examples today. Okay, so just to motivate why actually it's worth looking at complex fluids or simulating complex fluids. So complex fluids are basically in many situations around us in real life, and quite often, like if you think about a bottle of ketchup or a mudslide, the complex fluids flow more irregularly and very differently from water. So in order to understand the flow and be able to control it, we need to be able to model or understand at least how these fluids flow. And of course, this is also relevant for energy consumption when you pump suspensions. It's relevant for new applications like, for example, 3D printing, or I was thinking about self-cleaning surfaces where you have these droplets, such as droplets of mucus or some material which is not really clean. Maybe you just have water, but there is some dirtiness, surfactants. So you don't know really if a self-clean surface will work for all these different fluids. So just to reiterate, it's basically almost more fluids are complex than Newtonian from my point of view. Maybe it's just me, I'm so interested in them, but we have everything from chocolate to pharmaceutical products and paints and so on. And one type of complex fluids that I'm especially interested in is yield-stress fluids. So yield-stress fluids are basically something which can behave like a soft solid or a fluid, depending on the stress imposed on it. So if the stress imposed on the fluid is lower than the yield stress, the tau y here, then it will behave like a soft solid. And if the stress on it in some regions is bigger than the yield stress, then in those regions it will flow like a fluid. And one everyday example would be a toothpaste. So if you take a tube of toothpaste and if you hold it upside down, typically the toothpaste would not start falling out even if you have the gravity, because it behaves like a soft solid. So it's in its solid state. But if you start squeezing the tube, then you introduce some shear stress near the walls, which means that it will, the stress will be bigger than the yield stress near the walls, and it will fluidize and be able to flow out from the tube. So this is the kind of yield stress fluid with some solid regions and some fluid regions there. And of course, as I said, there is many different examples. One of them here on the left is carbopol. So you see a droplet breakup of carbopol, which looks quite different from if you think about water, for instance. And carbopol is a typical lab fluid because it is a transparent, so it is easy to make measurements on. Yes, so now we just talked about the fluid, but what happens if we put a particle in the fluid? So let's take the simplest possible example, particle sedimentation. So here I have a tabletop experiment that anyone can do, even myself. And we have water in one container and carbopol in the other. So let's see what happens when I put a particle which is heavier than both these fluids in the fluid. So of course it will drop to the bottom. This is water here. Yes, so let's see what happens when I drop it in carbopol. So now it actually doesn't go to the bottom, but it stays at a constant height. And this is because carbopol is in its solid state. So the gravity is not enough to cause a stress on carbopol so that it would be able to fluidize. So the carbopol cannot flow around the particle, and that's why the particle is stuck there. So we can see that we have a balance of gravity and yield stress here. However, it's not always that simple. We have also often flow. So here, if I introduce a flow by stirring the liquid, then I'm able to make the particle to settle. So now I have the balance between flow and yield stress. And one way to characterize this is the Bingham number. So here we have the Bingham number with yield stress on the yield stress above and flow speed below. And this would then be some kind of measure of the yield stress over the viscous stress of the fluid. And if Bingham number is large, then the yield stress is very important. So both the fluid and the flow are both important. So let's see now if we can model this very simple process. So the most simple physically most simple model is the Bingham model, saying that as long as the material is, the stress on the material is below the yield stress, it will behave like a rigid solid. And after, when we go above the yield stress, then it will start to flow like a fluid. So here we have a diagram with shear rate on the horizontal axis and shear stress on the, or stress on the vertical axis. And as soon as we are above the yield stress sigma 0, then we get, when we keep increasing the shear rate, we get a Newtonian-like behavior where the shear stress increases linearly with the shear rate. So this would be a Bingham fluid. It is not numerically always very simple to solve, but physically it's a very simple model, and it has been, there have been many studies using this model over the years. So let's see how it applies to this problem of one particle settling in carbopol then. So here we have an experiment. It's a particle in carbopol, and in this case it is obviously settling because there is a velocity field shown by these colored contours. So I would like to note two things about this velocity field. So first of all, it's asymmetric on both sides of the particle, so it's not the same at the back and at the front. And secondly, there is what we call a negative wake, meaning that it's more easy to see from the velocity field. This means that we have a reverse flow in the wake. And one might think that this is nothing special because often we have reverse flow in wakes, but here the Reynolds number is basically 0. So it cannot come from the inertia, it has to come from something else. So these are two experimental features that were seen in carbopol. So let's see what the Bingham model does for this case. So here we have the experiment, and then we have a simulation using Bingham theory. And we can see it's quite different. So actually we don't get at all this front-back asymmetry, and we get nothing like a negative wake. So it's not very satisfactory. However, in as late as 2016, Samopoulos group did this simulation using an elastoviscoplastic model, where you have both the yield stress and an elastic contribution. And now all of a sudden you get this, you can capture this effect. So you have the front-back asymmetry and you have this negative wake as well. So this is obviously much better. And think about this. So this was 2016 and it's only one particle settling in a still fluid. So suddenly there are many problems left to solve in both laminar and turbulent flows of these fluids. And a similar effect we also saw then when we did the simulation of a rising bubble in elastoviscoplastic fluid. So here also at low Reynolds numbers, the Newtonian bubble is completely round, whereas the elastoviscoplastic, the bubble in elastoviscoplastic medium gets this tail shape, which is asymmetric. And here you see experiments which are actually in viscoelastic fluid and they show similar shapes. So the elastic contribution is important. Okay, so how can we then include this elastic contribution? One parameter that characterizes the effect of elasticity in flows would be the difference between the ratio between elastic timescale and flow timescale, which is called a Deborah number or sometimes Weissenberg number. And what does this mean? The elastic timescale would be a timescale, if you think about these polymers like dumbbells, so they can store energy and then they can release the energy. So the elastic timescale is the time over which the energy is released. Depending on the ratio between this and the flow characteristics timescale, then we can get a lot of elastic effect or none. And equation-wise, how do we get this elastic timescale there? The most basic evolution equation that we can have is the Oldroyd B constitutive equation. So here we have the tau E is the extra stress tensor, which comes from the contribution to stresses from these dumbbells, the polymers. And in order to solve it depends on, it is dependent on where these polymers are. So we need to solve this evolution equation in time and in space all the time, together with Navier-Stokes equation. So this is the constitutive equation that one solves. And here we have the polymer relaxation time and then something called polymeric viscosity. And the polymers are obviously advected by the flow. And we get something with this upper triangle, which is called upper convective derivative. So it's a little bit like material derivative, but it also looks at the situation from a reference frame, which is also rotating with this together with these polymers. So this is the Oldroyd B model, and then there is many other models which are similar kind of extensions, such as Fene-P model and Gieseckers model, to name a few. Okay, so the idea how we develop this Oldroyd B model in order to take into account both plasticity and elasticity was given by Saramito in 2007. So he introduced in the Oldroyd B model a switch, which distinguishes between the solid and fluid states here. So as long as this switch is at the zero position, when we are below the yield stress, then this model behaves exactly like an elastic solid. So we get an elastic solid in low values of stress. But when we go above the yield stress, then it behaves more or less like an Oldroyd B fluid. So we get this material, which is elastic solid and viscoelastic fluid, depending on the stress. And we get a nice continuous transition between the two, which has been a problem with some of these earlier models. So then we just solve this together with Navier-Stokes equations. So we solve Navier-Stokes equations, and then we, in Navier-Stokes equations, we need to take into account not only the viscous stress and pressure, but also this extra stress, divergence of the extra stress. And how do we get that? We get it by solving the constitutive equation that I just showed you from the Saramito model. So this can be done, and we have shown in a paper how we do it for different cases. So in this DNS code, we can simulate three-dimensional elastoviscoplastic flows because it's based on our DNS code for instance, particle-laden flows in the past. So we just extended it with this elastoviscoplastic constitutive model. So we can do three-dimensional flows, laminar and turbulent flows. We can do particles with immersed boundary method and droplets with level set, for instance. And we have done studies on this, but I will not present them today. One important point here is that, of course, we need to solve for this elastoviscoplastic stress tensor, which has in 3D has 6 independent components. So we have 6 extra field variables. So we need to be quite efficient in general, otherwise it will take forever to solve these equations. So it's important to have a very well scaling basic Navier-Stokes solver, which we have because we have this A50 based pressure solver, which works also for density contrasted flows. Another option would be, for instance, multigrid, but one needs to have an efficient Navier-Stokes code in order to be able to do these calculations, even if we go to HPC clusters. And the other thing that we need to think about is the so-called high Weisenberg number problem. So this appears just like for viscoelastic fluids, that the constitutive equation becomes ill-conditioned when we increase the Weisenberg number. And this can be solved in different ways. Either artificial diffusion has been a common way. So in this group, and with Luca, we have developed a local artificial diffusion, which only introduces diffusion where it's needed. You see it in this figure here, without smearing out all the features in other places. And the second one way to solve it is the log conformation method, which is also a well-known method for viscoelastic flows. And we have implemented it for elastoviscoplastic flows and shown that it also works as well for those. So I thought I would now move into actual results. And I will start from the yield-stress fluid flow through a porous medium. And we have done a lot of work actually on this configuration in many different settings, but they have some common features. So the idea is that we have a flow through a porous medium. And the idea that applications are interested in is basically to find the relation between the pressure drop and distance for these complex fluids. So can we formulate something like similar to a Darcy law, but then it would depend on the complex fluid properties somehow. And one application that this may happen, and there are many others as well, is so-called cement grouting. So in Sweden, when you build a tunnel, then what you need to do is you are not allowed to drain the groundwater from the rock. You need to let the groundwater be, and instead you seal the cracks, and this is typically done by cement. So you put cement in all the cracks and hope that it's sealed, but nobody actually knows how far the cement goes. So this is unknown because cement is a complex fluid and yield-stress fluid. So it would be very nice to have more information about this. Okay, so in the first case, then we simulated just one periodic cell. So we assume that this would be an uniform porous medium, and then we take periodic boundary conditions. The flow goes from left to right in the white area, and these dark gray areas, they are solids. So basically these are the walls. And then we had two different configurations, two different geometries, one symmetric one and one where these walls are staggered, just to see if there is some effect of the geometry. Yes, and then what we wanted to do here is to look at the effects of elasticity also in this geometry. So we did one simulation with only viscoplastic flow with this Bingham model, which is solved by a method called Augmented Lagrangian method, used for many viscoplastic flows. And then we did elastoviscoplastic flow simulations using this new code. Here we have, as in many complex fluid situations, we have many dimensional parameters, from the yield stress, elastic time scale, polymeric viscosity, the inflow velocity, viscosity and density. And we get 5 non-dimensional numbers here. The porosity would be related to the geometry only. The rest are related to the fluid or the flow. But I'm going to focus on only 2 of them. One is the Bingham number here, the ratio between yield stress and viscous stress, which we have varied between 0 and 100. And the Weisenberry number, the elastic time scale over the flow time scale, which is we have varied up to 0.5. Yes, so let's look at how the flow can look like in this flow cell. By the colors, you see the velocity field. So only in the region where you see these colors, the fluid is flowing. In these light gray areas, these are stagnant regions. So here there is some fluid, but it's stagnant. So this is these are solid regions, basically. These are regions where it's a soft solid and it's not moving. So we could also call this fouling regions. And then we have inside the flowing regions, we also have solid regions actually. These have a different character. They are so-called pseudo plugs. So in these, the material is solid, but it's still moving throughout the region. So a little bit like if you think about a toothpaste, and in the middle of this plug, the material is solid, but it's still moving, squeezing out from the tube. So these pseudo plugs are similar to that. But here we get actually fluid constantly in this pseudo plug, and then it leaves the pseudo plug on the other end. So it's actually solidifying when it comes in, and then it is fluidizing again when it goes out. So let us compare then these elastoviscoplastic and viscoplastic flows. So what do we actually get? So we have viscoplastic flow in the top 2 figures, and elastoviscoplastic flow with low elasticity in the bottom 2 figures. Otherwise, the configurations are the same, and Bingham number is 10. So we see immediately there is some similarities, and there is also some differences, and in particular with these pseudo plugs. So even if we introduce just a tiny bit of elasticity with the Weisenberg number 0.01, these angular regions become bigger, and they have a different structure. They are not symmetric front and back here. So we see some differences. So let's see how this affects the pressure drop. So actually the answer is not so much. So at least in this regime that we have studied. So here we have Bingham number on the horizontal axis and the pressure drop over distance in the vertical axis. And we have 4 different results summarized. We have the viscoplastic in flow in both geometries in red, and we have the elastoviscoplastic flow in both geometries in blue. And we can see here that the results are not too far from each other, especially when you go to these Bingham numbers of around 10 here that I showed before. So here actually all the 4 results are very close to each other. Then in the viscoplastic simulations, we could also extend it to higher Bingham numbers, and there we can see a kind of linear relation between the pressure drop and Bingham number. But this was kind of intriguing to me, how we can get so similar results for viscoplastic and elastoviscoplastic when it comes to the pressure drop, even if the flow looked different. So the physical reason to this is mostly in that these fouling regions, the real stagnant solid regions, they have still the similar shape. So these are the ones that are important for the pressure drop here, because these are basically deciding how wide is the channel for the flow to pass through. So it looks like because these regions are similar, then we get a similar pressure drop. Okay, so this was just a very low elasticity. So now I'm trying to increase the elasticity here to see if this has some effect, and it does. Unfortunately, it's not such a nice scaling as for the Bingham number. So here we see a non-monotonous behavior first we get when we increase the Weissenberg number, first the pressure drop goes down and then it goes a bit up again. So we cannot make some general conclusions about the effect of elasticity here. And another thing is also that we see a difference in the flow character. When we start increasing the Weissenberg number, then the flow starts to oscillate, which is also interesting. Okay, I thought I would say a few words about more complicated geometries. So this is a paper that was very recently published in JFM. So I was very happy to see, actually yesterday, noticed that this was the cover picture. So I just had to put it there. So here we are doing a study of more complex and randomized porous medium and only viscoplastic flow here. And then we are also looking at the effect of surface slip, which is sometimes present in yeast fluids. Okay, so here we see more complex porous medium. So we have randomly placed spheres around this domain, and Bingham number is 10,000. And as you see here, what you see here is the velocity field. So actually we don't get this typical behavior for Newtonian fluids where you have these channels everywhere in the porous medium. You only get flow through these two channels shown here. So this is called channelization, and it's very typical for yeast fluids at high Reynolds numbers. It's very nice that we are now able to study this. And you see two different cases. Obviously, one is much more packed and the other one is much less packed. And you can see that these channels that the fluid takes are very different. Okay, so then let's see what happens if we introduced a little bit of sliding in here. So if we assume that the fluid, like carbopol, for instance, has a little bit of a slip on the solid surface. So others have previously come up with this model for yeast fluids and their slip on a smooth surface. So we have a slip velocity, which is introduced if the wall shear stress is bigger than the so-called slip yield stress. So we have a situation, if we think about this just in a channel flow. So we have a situation where at very small pressure gradients, we get no flow at all when this is a yield fluid, so it just doesn't flow. And then if we have a little bit more pressure drop, but so that the shear stress is less than the wall years, the wall shear stress is bigger than the slip yield stress, but less than the fluid bulk yield stress, then we get a uniform flow. And then finally, when we are beyond the bulk yield stress as well, then we get this channel flow, but with slip. So let's see how this influences the porous medium then. Yes, so here we see the same as before, but the figures on the bottom are for sliding flow. So as you can see here, for this case where we have a very packed porous medium, we get much more channels. So actually the channelization is delayed. So we have the same Bingham number, but we have many channels where we get flow, which is kind of intuitive because the resistance is a little bit less. On the other hand, in the less packed case, then we get more or less the same results for the two. So slip doesn't have such a big effect here, which is also intuitive because we have the channels are much wider. Okay. And now I'm showing a very crowded figure here, and it's intentional because I want to show you one particular feature. So we have here the Bingham number on the horizontal axis and the pressure drop over distance on the vertical axis, and then we have a lot of different results. So here we have results for four different packing ratios or porosities, and we have results for uniform porous medium. So this periodic case that I showed before, we have these random cases, and we have with slip and without slip. And in addition, we also have introduced some other people's results in 3D, Bauer et al. Results for 3 different porosities as well. And they are 3D and our simulations are 2D. So it seems like we have a universal scaling because you see that the slope is the same in all cases. So we have this slope of 1 in the log-log diagram in all these cases. So it really seems like the pressure drop universally scales with the Bingham number, no independently of the geometry or slip or 2D or 3D. And by the way, the geometry for the two geometries, the results were very, very close in this case. Okay, so I'm glad to conclude this part of the work. Obviously we get these solid regions in a gaseous fluid, and the solid regions size increase with the plasticity when you increase the Bingham number. But we get two different kinds of solid regions. The light gray ones here, which are not moving, which are the fouling regions, and the pseudo plugs, which are where the fluid is moving through. And the pseudo plugs are very affected by even a small elasticity, but not the stagnant regions. Plasticity decreases the permeability of the medium. We have the scaling of delta P over L with Bingham number to the power of 1 at high Bingham numbers. And then elasticity finally has a non-monotonic effect on permeability. And then we studied also effect of slip, and it can delay the channelization to higher Bingham numbers, especially in the cases where the porous medium is very packed. And if someone is interested in this channelization in particular, then we also have in the same JFM issue another study on where we try out a simple network model for the no slip case. It wasn't possible to extend it for the slip case, but for no slip case, we got very good results by predicting the first open channel when you start increasing the pressure drop over the porous medium. So now I'm moving on to the bubbly flow with surfactants and the effect of viscoelasticity on it. And this is a work that has been done together with my collaborators, Muradoglu group in Turkey, and also Daulet Isbasarov, who was postdoc with me, but now is in Finland, and Pedro Costa also now in Iceland. So the kind of surfactants that we simulate are soluble surfactants. So we think about these come from impurities that are added, or then we have just dirty water. So typically dirtiness is surfactants. And what happens then with these dirt particles? If they are distributed in the bulk fluid, then they start collecting on the surface. If they are absorbed on the surface, then you get a distribution of surfactants along the drop surface. And the surfactant local concentration, it lowers the surface tension locally. So if you get a non-uniform distribution of surfactant, you get Marangoni forces, and therefore also then the Marangoni force will influence your flow field. Okay, so one more effect that the surfactants may have if they are in the bulk is that they make the bulk fluid viscoelastic, because they are also long chains molecules and they can behave like dumbbells, so they can actually store elastic energy. So it's a valid question also therefore to ask what does viscoelasticity do for these surfactant-laden flows? Okay, so the flow setup that we have chosen is taken from an experiment by Takagi et al. And here we have a vertical channel, and the bubbles go up the channel, of course, by buoyancy. But then also we are forcing the flow against gravity up in the channel. And this is somehow relevant for these results, especially for the shear induced lift force, to which direction it goes. Okay, so this is the flow setup. And let's just think for a moment what we would expect to happen here. What kind of physical forces do we expect to exist in these simulations before we have done them? So this figure is from an earlier study that we did for one bubble in surfactant-laden bubble in a channel. So here we got the result, which is kind of also known that we have, when the bubble goes in the same direction as the fluid, we have shear-induced lift force, which acts towards the wall. And then we have Marangoni force, which in this case acts towards the center because of the surfactant distribution around the bubble. So this we know from the previous studies. And then it was the question, to which direction does the elastic force contribute? So in most cases, it has been studied in low Reynolds numbers, and it's well known, for instance, in microfluidics that elasticity brings the bubbles towards the center. So this is an old result, and then sometimes they form these trains like in these simulations. There has been one paper that we have found that says that the force should go also towards the wall in some cases. Okay, so we're not sure, but we would expect the elastic force to be direct. Okay, so just I want to look at the experimental result first, because this is the kind of the reality. So here we have clean water without any surfactant, and you see that the bubbles are more concentrated towards the walls than in the center of the channel. But if we add surfactant, then the more surfactant we add, the more uniform becomes the bubble distribution. So we get more and more bubbles in the center of the channel instead of at the walls. And this particular figure is with surfactant called pentanol. And so we wanted to first be able to capture this effect in numerical simulations, and also we want to study what is the effect of viscoelasticity. Maybe viscoelasticity has also a contribution in this. So we did two different cases. The first one is, we call it a small case. It's small in all kind of ways. It has a smaller Reynolds tau in a single phase. It has a smaller number of bubbles. And then the surfactant properties, they are taken from a computational study by Muradoglu and Tryggvason in JCP 2014. And the second case is what we call experimental. So here we have a bigger Reynolds tau, we have more bubbles, and most importantly, we take the surfactant properties of Triton X100 from Takagi et al. The experiment. And again, we get actually many non-dimensional parameters, so I cannot really focus on all of them. But we have anyway them in this table for the two different cases. So we can just focus here on maybe on the Weissenberg number here. So we get we have different Weissenberg numbers between 0 and 10. And then also this Langmuir number, which shows how well the surfactants are absorbed, are also different for the two surfactants. And this has a significance, as we will see. Okay, so now a little bit about the flow equations that we are solving in this case. So now we have again incompressible Navier-Stokes. We have again a viscoelastic contribution here, the extra stress. But then we also have a surfactant contribution, which consists of surface tension, which varies with the along the surface, depending on surfactant concentration gamma. But then we also have Marangoni stresses because of the gradient of the surface tension. Okay, so the viscoelastic stresses we get from Fene-P model, which is similar to the Oldroyd B model I showed before. But here we are limiting the extension of the polymers to finite values. So it's a little bit more realistic. And for the surfactant, so now, because it's soluble surfactants, we need to solve several equations here. We have a bulk concentration in the bulk fluid, which is the big C here. So we need to advect this. And then we need to also solve for the interfacial surfactant concentration gamma. And then, of course, we need to somehow exchange surfactant between the bulk and the interface. And here we have this equation here where we have absorption coefficient Ka and the desorption coefficient Kd. And finally, the equation of state, which shows how the surface tension is varying with the surfactant concentration. And just quickly about the numerical method. So this is not level set as we had in the other code. This is front tracking method, the same method as used by Muradoglu and Trygg was on JCP in 2014. And the advantage of having a front tracking method here is that you have Lagrangian points on the surface that you are following. And therefore you have a very accurate representation of the surface location. And also you can quite easily study the surfactant movement along the surface with this, because you have these Lagrangian points which are already on the surface. Okay, so let us look at the results. So first of all, we have this pentanol-like surfactant, which was the one where with the computational parameters from JCP. And we have surfactant concentration increasing from left to right. So in the leftmost figure, we have bubbles which are concentrated on the walls. And here there is no surfactant, so it is a clean case. And then surfactant concentration increases to the right. And in the rightmost figure, we have more uniform bubble distribution, just like we expected to have, and just like we saw in the experiments. So qualitatively, we get the same behavior here. So now the next thing I will introduce the viscoelasticity. And as I said, in microfluidics, and so we expect that the bubbles would go more to the center with viscoelasticity. And this is what happens. Yes, so here we have again, now we have Weissenberg number 5, bulk fluid, and then we increase the surfactant concentration from the left to the right. And surprisingly, the bubbles are still clustered around the walls. So it looks like here, actually viscoelasticity is promoting the bubble clustering at the walls and not at the center. And we were thinking about this a lot, and the explanation that we have found, because this is something that we see in all our simulations at different parameters. So it's that the FNP model is a little bit shear thinning. And because it's shear thinning, then it increases the inertial effects near the walls. So we get more shear-induced lift force because of this shear thinning. So this is the only explanation there can be. Okay, now let us anyway look at the experimental parameters, because these should be more realistic. So now if we look at the viscoelastic flow again, and we have no surfactant on the left and with surfactant on the right. So now at least in this case, when we have this Triton X100, very powerful surfactant, which is well absorbed. So even if we only have 0.1 ppm of this Triton X100, it still makes the bubbles go back to the center. So now in this case, we get actually the surfactant effect that we expect, even though the bulk fluid is viscoelastic. So it seems there is a big difference between Triton X100 and this pentanol or the computational surfactant that we had. And the main difference is due to this Langmuir number. As I said, that in this case, the surfactants are more efficiently absorbed on the surface. Yes, and if we want to look at the flow structures a little bit, so without surfactant, when all the bubbles are at the walls, then basically the turbulence disappears. So we only get these vertical structures near the bubbles. Whereas when we have this Triton X100, then we get turbulence across the whole channel as usual, and sustained turbulence. And about the flow rate then, so it turns out actually the bubbles, they are creating drag. And so here we have time on the horizontal axis and the velocity, flow velocity on the vertical axis. And the simulation is done in the way that we keep the pressure gradient constant. So this means that if the flow velocity increases, then we have less drag. So we start from the same as the single phase case. And then first of all, these bubble layers form, and then in almost all cases, then we get much lower flow rate at the end. So actually we get a drag increase in all cases. But when we introduce this 0.1 ppm surfactant, the Triton X100, the experimental one, then actually we get much less drag increase. So the flow rate comes almost back to the single phase level. So in these ways, we can also influence the drag in the flow as well. So we have seen in our later preliminary studies that we can actually, by introducing this surfactant, we can restore the polymer drag reduction in bubbly flows to almost the same level as single phase flows. Okay, so I will just show also in time how these bubbles behave. So if we have no surfactant at all and viscoelastic flow, then what we get here is the bubbles quickly go to the walls and form these clusters. If we have the same Weissenberg number, but 0.1 ppm of Triton X100, then first the bubbles are going to the walls, but as soon as they start absorbing the surfactant from the bulk, then they come back to the center. So this brings me to the conclusions of this turbulent bubbly flow. So we have been studied the combination of surfactants and viscoelasticity here. And the main conclusions are that clean bubbles move toward the wall because of the shear reduced lift force. Contaminated bubbles, however, they move toward the center because of mainly because of the Marangoni force. Viscoelasticity, on the other hand, here, the elastic force promotes formation of wall layers. So it brings the bubbles back to the wall. And then depending on what kind of surfactant you have, they will either form wall layers, or if it's a strong surfactant, then they can also go to the center. So this was all I have time to say today. So thank you for attending, and please ask me if you have any questions.
Great, thanks, Outi. Are there any questions from the audience? Best is just to unmute yourself and ask a question.
Hi, Outi. This is Prash Faluri from Edinburgh, actually. Hi, how are you?
Yeah, I'm good as you can be in this situation. Yeah.
Good. Nice to see you again. I had one question about the first part of the talk, if I may.
Okay.
This is about you mentioned about the slip yield stress.
Yes.
And so my question is, how do you set a slip yield stress? Is it something that is calculated experimentally? I mean, what does it actually mean as well? Yeah.
That is a very good question. So this model, I think it has its experiments in very simple geometries that are behind this model that has been proposed, that I showed to you. But then, of course, your question would be how to choose the parameters of the model, I guess. Let me see if I can. I will just try to get back the slide. It looks like I need to. Okay, now maybe. Do you still see the slides, or?
Not yet. No.
Not yet. Okay, I'll just try to go back. But I mean, the short answer is really that I guess no one can really see if this say that this always works or doesn't work. So it has been done for carbopol and in simple flows, but whether it always is a good model, we wouldn't know. But what Emma did in this paper also, so he studied several different flows with this sleep model, and he tried several different values, and it didn't seem like it had a qualitative influence on the flow. But of course, I mean, you have this all this behavior from not having any sleep to having a lot. Yeah, but how? I mean, it's really just. I mean, you would have to do these experiments and measure for the fluid that you are thinking about. I wouldn't be able to say anything general. So if for carbopol, it's known that it has this kind of behavior, but some other yield fluid might have another behavior also.
So Outi, am I correct in suspecting that if I if I increase my, if I choose another slip yield stress,
Yeah.
does that actually increase the channeling?
Yeah, I mean, of course, if you to put it to, you can put your, you can have, if your slip yield stress is the same as the actual yield stress, or you can go from everything in between the actual yield stress, the bulk yield stress, and having no slip. So of
Right.
course it would, you could get any scenario in between.
Right.
So yes, of course it would influence.
Yeah. Thanks a lot.
So you can get the channelization like in the no slip case, or you can get the one that we have in the slip case, or maybe you can increase the slip a little bit more, because I think most of the cases he just concluded he did them with one value of this slip
Right.
stress,
Right.
to get the
Right.
qualitative effect.
Yeah. Thanks a lot, Outi. Thank you.
Now that we have this slide up, can I also squeeze in a question? If you introduce these discontinuities in the boundary condition or in the material behavior, is there any chance for some kind of numerical oscillations between these two regimes, where you get some stick-slip oscillations going back and forth between two regimes?
It is also a good question. So this is kind of a different numerical method also. This is an augmented Lagrangian method, which is typically used for steady states. Yeah. And also what you see in here is steady states.
But if
so I guess there would be a possibility, for instance, that it doesn't converge because of these issues. But it didn't happen to us in these calculations. But yes, I think in general case,
But if you have unsteady flow, or you have independent flow, and it comes to a point where there are regions in the domain where it changes from one material behavior to the next, would it help to introduce like a hysteresis of some sort to get around, so that it doesn't really oscillate around this regime all that much?
Possibly. So we haven't even tried time-dependent flows with anything like this, because of it was augmented Lagrangian method. But of course, it would be very interesting to try time-dependent flows, and then the question is very relevant.
and then see what happens. Yeah.
Yeah. Exactly.
Good. Are we? Do we have any other questions from the audience? Please just unmute yourself and.
Okay, Peter, may I ask a question?
Yes, Shusong, please.
Yeah, hi. Okay, yeah, very interesting. Of course, very rich behavior. Because you have a lot of parameters and different models. So my question is right general. So here you have a origin B and its improvement. How universal it is? No, how widely it covers. And if you want to set the parameters, do you do calibration, with particular fluids in mind? It seems a kind of very vast territory, and
yes, I mean it is. Unfortunately, it's as we saw in this particle sedimentation case.
Yeah.
So it's a very simple flow, and still it wasn't modeled until recently. So there is always these questions that you get in the complex fluids. You get some experiments, you have some behaviors, and then what kind of model should we have to capture these behaviors?
Yeah.
So before this simulation was done with the elasticity, other people were suggesting maybe it's thixotropy, maybe it's something else. But then just by doing the simulation, then they could show that, okay, if you include elasticity, you can get quite good agreement. So this is unfortunately the way. So if you get agreement, good, but if you don't, then you have to think about what is the missing effect. Of course, all these models, they are getting a little bit, there are new models coming up all the time. So then we can simulate more kind of fluids, and then only then you will be able to compare actually the experiments and the simulations for a certain model, and then you can say that it only applies in some situation. So for instance, for this Saremito model, so we know that it actually doesn't have some of the properties that ESS fluids have. So one is that they typically are shear thinning in the case when they have when they start flowing, they are actually shear thinning. So the stress is not increasing linearly with the shear rate, like in this model. But Saramito has come up with a model which solved this problem. But then there is also other things like this thixotropy and time-dependent changes in the yield stress, for instance. So there are all the time are new models coming up which are supposed to capture more of the behaviors that one sees. But I think, as you saw, this agreement in this case for the settling particle, it was still not perfect. Maybe I can show it again. So if it would be a Newtonian flow, I don't know, boundary layer or something, we would not say that this is a very, very good agreement. The contours are still not, they are not identical with the experimental ones somehow. It's just that they are capturing the main trends.
Quantitative,
Qualitatively, exactly.
Okay, with this second part, you have this bubbly flows, turbulent flow. So you mentioned the interface. So you are tracking all the bubbles, right?
Yes.
So you have multi-connected regions. Do you allow for bubbles to burst or merge?
No, in this case, because it's a front tracking method. So if you try to, if you want the bubbles to merge or break up, then it's a little bit difficult to handle this method, because you are basically, you put all the Lagrangian points on the surface. And if you want this to be not one surface, but two surfaces, you need to do something in that case when it should break up.
Sure.
So, I mean, Tryggvason and companies, they are developing methods
the
for
bubbles,
this.
they come together very close. So you do nothing, you just...
No, so in this method, we would not see anyway, but also with the surfactant, we have this property that they also, because of the surfactant, they wouldn't merge. But in this method anyway, if they come close, they would not automatically merge. So we would need
physically
to
they wouldn't merge. You mean there is a physical effect preventing bubbles from merging? Or...
No, more like numerical effect. There is,
right, okay.
It's different if we look at this. We have used the level set in other studies. In this case, you have the level set field, which has actually it doesn't distinguish between one bubble and the other, and then they can automatically merge and break up, but not with front tracking. So
you have
come with some advantages.
Sharp interface.
Sorry?
Your interface is sharp.
Yeah, for front tracking, yes.
Yeah.
Good. Any other questions?
Yes, I have one. The experiments by, was it Tagaka or
Takagi? Yes.
Yeah, Takagi. Yeah. Are those initially viscoelastic fluids, or it's water with lots of surfactant?
It is water. So this was just a motivation from my point of view, was just that actually when you put surfactants in the bulk fluid becomes a little bit viscoelastic. So that's why it makes sense to actually include this effect in simulations.
Yeah,
but,
that's my question actually. If you to make it viscoelastic, how much surfactant do you need to add? And if you add beyond the critical micelle concentration, then you're going to get phase changes and all sorts of things that are not modelable the way you did them.
No, that is a good question. Of these surfactants, I don't actually know how much you would need to add. I know that people do, some who do, for instance, at KTH, they have done some experiments in viscoelastic flow where you put surfactants in order to make it viscoelastic. But I don't know exactly I don't know how much you would need to put. So it's more like a motivation, but not, but it's a good point. I should somehow make sure that I know exactly how viscoelastic these are, the surfactants that we are studying.
Yeah, I mean, the only issue is if you have to go above the critical micelle concentration.
Yeah, I wouldn't be sure actually. I don't know. No.
Okay.
Good question. Yeah.
Thank you.
All right. Are there any more questions?
Yes, please.
Yes, go ahead.
Thank you for this presentation. This is really a remarkable simulation, and I really enjoy this work. I want to ask a technical question: how you handle the local value of the viscosity for really low shear rate? I mean, when you said that the fluid can behave as solid or fluid, but when you have a really small shear rate, what is the local value of the viscosity?
Well, it's so I'm using these equations to model it basically. So yeah, I have the Navier-Stokes, and in Navier-Stokes I have the normal so-called solvent viscosity. So this is there also with at the low shear rates. And then in addition, we have this polymeric viscosity in the constitutive equation. So the viscosities that you would measure would be a sum of these two in general. So I'm not quite sure how to, maybe I don't understand the question correctly.
No, it's just because when it behaves like solid, it's mean the local viscosity is very high, and I was just
you mean, okay, but we don't really model it in that way. So this is one way. This would be the, if you think about the Bingham fluid,
yeah,
you can model a Bingham fluid by making it, I mean, physically, one way to model it is a Papanastasiou model, where you basically make it a the solid is a very, very high viscosity fluid.
That's what I was thinking. Yeah, I thought you were doing this way. Sorry then. Okay.
No, it's no problem, but this is a good question. So actually what we do is we say that it's an elastic solid. So it's not a fluid with a very high viscosity. It is an elastic solid.
Yeah. Okay. If I can add another question. Sorry.
Yes, go ahead, please.
Yeah. You mentioned the equation of state, how the surface tension depends on surfactant, and you put something like in between. You have a relation and I think a boundary for a maximum value. And does your simulation hit the maximum value of this surfactant? So
no,
requires to put this boundary, or just why not using directly the Lagrangian equation of state?
Let me see here.
Yeah, this one.
So
yeah.
here. Oh no, it doesn't really show.
Yeah.
The equation.
So what is the value of epsilon sigma on the last?
So basically, in the simulations that we have done, we are never close to the maximum concentration. So we are somewhere. I think the model breaks down before this. So it's actually not okay to be close to the maximum concentration. So if I remember something, we are never more than 30% of the maximum concentration.
It's quite enough,
yeah.
Yes, we saw this because we do some surfactant here in the group, and sometimes it's true that we could reach a really maximum packing, and the surface tension can become negative. And and I was just wondering, what is the value of the epsilon you're doing? But I think it's the same.
Yeah, I would need to check. I don't really remember. Yeah.
Okay. May I ask a question? Kind of promoted by the previous question, if I understand it right. So you have this model, you have this equation for stress, just the previous one, they connected with when you are answering the previous question.
Okay, so the elastoviscoplastic.
Yeah, so you have this yielding stress. I thought the question was about, you have three-dimensional case, right? This yield stress. You can understand it in kind of a one-dimensional setting. If you have a three-dimensional situation, is it kind of principal value
You mean this
more generally,
norm, yeah.
is this question kind of a coordinate independent? So okay, if you rotate your coordinates and you get the same thing, isentropic. So does this equation obey the principle for coordinate invariance or independency?
I mean, I'm
no, it's a
not really
material
sure of how I have
independent or not. Of course, I don't know. I don't have a preference. I just want to know whether.
So in
Yeah,
what would be the physical situation that I should have in mind to? I mean. Coordinate independency. I mean, it's if you rotate your coordinates, you certainly would have the same stress tensor but different components. I mean, this is the question.
Yeah.
So it is a physically motivated equation. Yeah. Physically correct. So, but maybe your question was, I thought maybe your question was about this norm.
Yeah, maybe this. One is is particular of
so this is basically
may destroy something maybe.
So this is actually the von Mises criterion. So it's a two norm of the deviatoric part of the extra stress tensor that we have here. I should have probably written it out. So this is how it generalizes also to 3D.
I see that. I see the idea, the motivation for doing this. Just what kind of principle we need to stick with in doing so.
Good. Are there any more questions from the audience? No? No more questions? All right. Then we can close out the seminar. I want to thank Outi again for that very, very nice talk.
Yeah,
and,
very, very impressive. Thank you.
Yes.
Thank you.
I hope to welcome you back for next Friday, same time, seminar by Dave Smith from Birmingham. All right. Thanks a lot.
Thank you.
Hi, Trevor.
Recording.
We muted.